Well, good news is that it is my last lecture, so you will be not tortured anymore with formulas and modeling. Bad news is actually still 50 minutes to go of this. Last time, 2 days ago, I sort of like explained to you and proved to you that if you don't like to engage in procreation activity, which is elaborated version of having sex, so if you don't want to do this in front of your in-laws, then unfortunately the whole population is doomed because it will follow the Ricker's curve, which is essentially overcompensatory, and therefore there will be very small population at the end. A good news about this is that we're talking about a single equation, and I told you a single equation can model something which doesn't interact with the environment. But fortunately, in our case, we can kick out our in-laws and enjoy. Okay? So this leads us to systems of differential or difference equations. And essentially, this is a doubling of the picture which I showed you at the very beginning. So essentially, we have two or more populations, let us say, and each of these populations can follow a standard rule as before. So we can have this creation, so birth, death, inflow, outflow terms. So each population can follow along this route actually itself, but also they act upon each other like this in some way. And our main topic today is, in some sense, to understand the meaning, the nature of these interactions in equations, in systems of equations. Okay. Again, in the first approximation, typically we split our equation into, let us say, 4 blocks here, 2 blocks for each equation. So first, of course, we have the rate of change of P1 without the presence of P2, or the rate of change of P2 without P1, and then impact of P2 on P1 and conversely. Okay, of course, this can somehow impact also somewhere here, because, for example, birth rate can depend on the presence of the other species, but this is sort of like a rough division. And also it's done mathematically, where we simply, even artificially, if you have very general formula for the interactions, we can artificially split this equation into 2 parts. And P1 and P2, okay, so there are densities of the populations over a certain area. In the first term, in each line, we can use any of the models, any suitable model which we discussed earlier. So in some sense, even if we are talking about systems of differential equations, the last 2 hours have not been wasted, because essentially there are building blocks which go into this equation. So we presented building blocks which go into the system of equations. The second 2 terms require some attention. And again, the simplest model would be simply to consider a linear influence of P2 on P1. It is, of course, oversimplification. You can easily, okay, let me see what I have here. Okay, so we will return to this a little bit later. Even in this simple model, we can understand what is the relation between the signs of these 2 terms and the type of interaction these 2 equations describe. So for example, here we can see that if A1, 2 is positive, population, as we said earlier, is always positive. So this term positively contributes to the growth rate of the population P1. So the presence of the second species, let us say, has a positive impact on the evolution of the first species. And so on. We can actually, typically you subdivide this into 3. Yep. Uh-huh.
There's a dimensionality issue. So what is the dimension of the coefficient A12?
Well, the answer is so that actually it agrees. So it will be, for example, 1 over, so it will be some rate. It will be 1 over.
P1 per unit time.
Yeah.
P1
Yeah.
per unit time times P2.
Yes. So I mean, of course, the dimension I didn't, then would be another hour at least of lecturing if I wanted actually to play with correct dimensions. But yeah, we need to take into account that the dimensions are the same everywhere in each term. So essentially, as I said earlier, we have 3 typical types of interactions in systems of 2-by-2 equations, so describing interaction between 2 populations. If both coefficients A1 and A2 are negative, then it is clear from here that P1 has negative influence on P2 and P2 has negative influence on P1, and therefore we have a competition between 2 species. Okay, so it's a competitive system. If one of the coefficients is positive and the other is negative, then it was what? A12, okay. So A12 was positive, that is P2 has positive influence on P1, but P1 has negative influence of P2. So it's typical predator-prey interaction. So in predator-prey interaction, the presence of predator is detrimental to the prey. The presence of prey is beneficial to predator. And then we have so-called mutualistic relation when actually each species benefits from the presence of the other, for example, symbiosis. So these are typical basic classification of equations like that. And let us, for a moment, focus on the predator-prey case. The model, just let us try to understand the meaning of this term, linear term. It means that the predator, it's a single predator, it's the same amount of prey, whatever the circumstances. It's simply alpha times P2. So one predator, it's alpha per year, for example, of prey. And then the total, well, not contribution, negative contribution actually will be alpha times P2. Okay, so this is unrealistic, of course. And then we need some nonlinear interaction here, nonlinear type of interaction. And as we have seen many times earlier, the simplest nonlinear term which we can use is so-called mass action law, the term borrowed from chemical kinetics. So at least here, there is some contribution of prey to the rate at which this prey actually is devoured. Okay, so roughly speaking, the interpretation of this term is more or less like that. I'm a single predator, so P2 is 1. And for example, if in this room is only one individual, one prey, I will eat this one. Maybe first probability half, if the prey actually is nimble enough to escape me. If there are 2 individuals, then I will 2. If there are 10, I will eat 10. If it's 1,000, I will 1,000, or half of the 1,000. Okay? So as with epidemiological modeling, this assumption makes certain sense if the densities are small, because indeed, if I'm very hungry, and if I have here 1 cutlet, I will eat this cutlet quickly. If I have 2 cutlets, actually, I will also eat. 3 maybe, but if I have 10, probably it will be a little bit more difficult. So there must be some saturation here. So this is a very popular term in modeling, but of course it has its limits as any model so far. But this is a system, just one of the most typical systems of interaction between 2 species, which you can write down. Most classical books actually, especially doing ODEs rather than exact modeling, actually will concentrate on this type of models, because you can put into this model a lot of stuff. Just to mention, as you remember, if, for example, alpha 1, 2 is negative, that it means that y has negative influence on x, which means that y is a predator type and x is prey type. Now, these terms here can model behavior of the prey population with respect to, well, without the presence of predator. So, for example, if we put mu1 negative, so it will be beta1 minus mu1x, then it is a logistic growth. If I put mu1 equal to 0, then it is exponential growth of the prey. If I, for example, put beta1 negative and mu1 positive, then this can describe some sort of like sexual reproduction within prey, because then the rate of birth will depend on the product, like mass action law again. So it will be x squared type in the birth term, and so on. So we can put a lot of stuff into this simple model, a lot of typical interactions. Okay. Now, it is clear that, as I said earlier, that in modeling of interactions of this type, mass action law is a very simplistic point of view, because there must be some saturation effect. I cannot eat as much really as I would like, especially if we are talking about sort of like lion and zebras. Yes? And then a typical way of modeling, again, one of the simplest way of modeling this saturation effect is something, this was done by Holling, and he simply assumed that the population of predators can be divided into two groups. One is actually searching for prey, hunting, the other is handling the prey or eating. And this takes some time, especially if you are successful enough to hunt, for example, a buffalo. Then it will take some time before you start being a predator again, active predator again. So the assumption of Holling, the starting assumption of Holling is written here. So the first assumption is classical linear assumption. So TH is the hunting time. So we take some long time, capital T. TH is handling time per unit prey. Okay, so for example, if I catch a unit prey, then I will be busy for TH. Okay, if I am able actually in this time T be successful in my hunting twice, then here it will be 2 times TH and so on. So, and C is some, of course, as usual, proportionality constant. So this is the amount of prey consumed by a single predator in time T. So it is essentially C times, sorry, let me see. Yeah, spent on hunting. Sorry, I said handling or hunting. So this is TH is hunting time. So I have effective hunting time, which is smaller, usually smaller will be then time T over which I observe the, let us say, the system. Okay, so now, what is TH? Holling assumes that there is no other distractions for a predator. So either it's hunting or eating. Therefore, well, the mass action law assumes that hunting time is the total available time, the observation time T. But if there is finite time used on eating the prey, then TH will be the total time minus the time during which I eat a single prey times the number of prey I caught. Yes? So if I, for example, I observe the environment for, let us say, a year. Okay, so capital T is 1 year. Let us suppose that I eat my prey during 1 day. Okay, and then I, for example, catch 20 antelopes during the year. So here will be 20 days. So I can only hunt for 345 days. So this is the hunting time. So this is the argument of Holling. And then, when you solve this equation for P, you obtain this term, which is quite familiar to most of us, something which is called the Holling type 2 functional reaction. So this is the number of prey per unit time. And then this actually leads to the formula for this nonlinear interaction. So instead of, if you are talking about Holling type model, then here instead of x times y, you will put this term xy divided by 1 plus constant y. So this is how this Holling type of reaction is derived. Of course, quite often you can assume mass action. For example, and now it's a model especially for Urey. Again, we will go to Ricker's equation. And Ricker was a visitor in their institute some time ago. So for example, if we are talking about, it's somewhere here probably, for example, it's a typical example of cannibalism when adult salmon very soon after spawning actually eat offspring. So you can imagine the salmon is a big fish, offspring is like that, so essentially salmon can go like, like tornado through. So it doesn't stop to eat, really. So here we can assume that we have mass action law. And let us try to model evolution of the salmon population. So, sorry, actually, I think this one. Right, okay. So, we consider a model describing the size of a salmon population at the end of each spawning cycle. We assume that breeding occurs yearly. The time between breeding seasons will be sort of like measured in continuous time. We assume that the adults live for very short time after breeding. This is actually the case for Pacific salmon, but not Atlantic salmon. But the final result actually is the same. Constants are different. So now, capital PK denotes the population of adult salmon immediately after the end of spawning. And thus, spawning season K, and thus at the beginning of the season K plus 1. And let us zoom onto this season. You know, during this spawning, the adult salmon produces larvae, and not all larvae become adult, and the prevalent cause is cannibalism. Actually, as I said earlier, adult salmon actually enjoys eating its offspring. And this is the prevalent case in this very short period of time. And because of the difference in size, it is actually quite reasonable to assume that there is mass action law. So if PK is the density of, I think it should be somewhere here, the density of larvae. So we have here, this is the rate of eating. So classical mass action law is product of the density of larvae times the density of adult salmon times, of course, proportionality constant and something like that. So this is actually the death process within this short period of time. And we assume that practically adult salmon during this time will not die. They will actually drop dead at tau. And therefore, using initial condition, we obtain that the density of larvae at time t, by solving the previous equation, this capital PK here is a constant, yes, because it is just at fixed moment in time. So I solve this equation. This is a linear Malthusian equation with constant coefficient at this particular time. And then I assume, okay, that's fine. Okay, that's okay. I think it is okay. So when all adults are gone, so after time tau, not all larvae survive. And again, we take exponential death rate. So Now, what is the relation between the population of adult salmon at the beginning of the next breeding season? Just what happens? We have a population, capital PK. This population produces beta PK of offspring. A proportion of this offspring first is eaten by adult salmon. The adult salmon drops dead. So at the end, we have e to the power minus lambda tau PK of larvae. And these larvae actually die at the rate of gamma. Okay, so the fraction gamma of larvae which were present after this frenzy of cannibalism survive. Okay, so this is now the population, the adult population, because the larvae become adult at PK plus 1. Okay, and this is what you have here is the Ricker equation. So this is equation which can model in which mass action is used to derive from something which is called either hybrid or impulsive system, a discrete system describing the size population from year to year before the breeding season. Okay. So this is one of the case studies which I wanted to show you. And now I would like actually to talk, because it's quite a lot of epidemiology here, so we can talk about two aspects of epidemiological models. And first aspect actually is sort of like continuation of the discussion of the Holling type 2 predator. I will show you how to derive a similar general contact rate from Holling type argument. Only here it will be a little bit more complicated. Okay, so I think I don't have to go maybe through the constants because it's more or less the same as before. We are talking at this moment about general SIRS model. So we have diagram like that, which translates into the system of equations of this type, which you probably, most of you who didn't sleep during the Abbas and Andrea lectures must have seen. So interpretation of lambda, nu, mu, and so on, b are more or less obvious. We will be not talking about the birth rate here. What I will concentrate upon is how to model the contact rate. We have seen so far two typical contact rates. One is classical mass action, so it's lambda times or beta times S times I, or we have seen frequency dependent beta times S times I over N. Okay, this part is not maybe that important. Okay, so this is the mass action law. Sometimes it is okay, sometimes it is not. Now to actually more sort of like detailed modeling. So we make the same assumption as in Holling model. So the problem again is that I move into the population of susceptibles, okay, and typically, you know, it takes time to infect ABA.
Absolutely.
Yeah. So I cannot immediately infect my lean.
Yeah.
I must spend some time infecting ABA. So there is actually shorter time than expected during which I can infect somebody. Okay? And then again, the assumption is that I either am busy infecting somebody or looking for somebody to infect, in the same way as predator prey population. So to infect somebody, I must form a pair with ABA. Okay. So, okay. So we divide now the population into singles and pairs. Okay, and Cn is the fraction of pairs engaged, so fraction of the population engaged in contact. So Cn here is precisely the fraction of the population, so the number of pairs will be half of the fraction. So this is density, and I multiply everything by the total population, and so this is now the real number. And then this is a random mixing, so the probability that in the pair you will have one susceptible, one infective, which is necessary for infection. We are not talking again about co-infection, something like that, so this is the simplest model. The probability that in this pair I will have a good pair from my point of view as an infector is S over n times 1 over n. Yes, probabilities of finding infective and susceptible and bringing them together. Okay, so the density of pairing that potentially can lead to infection is Cn Si over n. And of course, I can put here some constant, proportionally constant. Now, the function Cn may be quite general. Of course, should be non-negative, should be non-decreasing, should be linear for small n to recover the mass action rate. Yes, so as I say, for small populations, we accept that mass action is more or less correct description. And then it must tend to a saturation limit, which must be, of course, smaller than 1 or equal than 1 as population grows indefinitely. Okay, so let us try to derive such a function using a Holling type argument, as I said earlier. As before, in the population of size n, we introduce the number of singles and pairs. So n is equal to x plus 2p. And then, of course, just rewriting the previous equation, I put here pairs times 2, because these are the actual number of individuals engaged in contact. Yes, not pairs. Okay, so essentially what I am looking for is the formula for the number of pairs at any given time. Okay, so repeating what I said earlier and introducing notation, TH will be the time duration of a contact, average duration of a contact. Z is total number of contacts over some time t, and Y is per unit time, the number of contacts. So the first step is like in the Holling argument. So the number of contacts per unit time will be the number of singles, available singles, times the available time. Okay, times effectiveness of infection. Okay. Now, the problem here, and this is the difference between this derivation and the derivation in the Holling type argument. Prey is unlimited. Here, the number of x actually is also, because x, I am x whenever I'm not sitting here. So these two terms actually are related. In Holling argument, this was completely independent of this part. So I have actually to recalculate the number of singles. Again, a single is when I am not engaged in contact. So it is essentially the same type of formula. Okay? And then, for a given single in time t, it is available for the time it is not in the contact. So this is typical time during which a single is available to make another contact. So for fraction 1 minus yth of the total time. So this is the fraction of time the single is available for contact. So in other words, it is a probability that if I pick a single in the sort of like in the total population, this single will be available for contact. Now we have to translate, for those of you who know mathematics, this is essentially ergodic type argument. So we can translate the frequency in time into frequency in the population. But it can be done, in this case, very easily. So what is the number of available singles? Particular single, so we have total population capital N, and a given single, okay, so this is, okay, so the total number of available singles is an average over the number of available singles times the probability that you have this number of available singles at a given time. Okay, it's classical expected mean value. Okay, you have number of singles is a random value, random variable. So the expected value of the random variable is the sum of the value of this random variable times the probability that this random variable is taken, okay? So this is precisely what is happening here. So P is the probability that a given single at a given moment is available. So I have k available singles with probability. Well, I have p to the power k. I have to have k singles available, and they are available with probability p, and the other must be not available, okay? So this is 1 minus p and minus k. But then I can have a number of possible combinations of this. And this is actually given by binomial symbol. And therefore, this is the expected number of available singles at a given single time. This is essentially similar, very similar to what I did yesterday with, 2 days ago with Poisson distribution. And now by some algebra, which I don't want actually to bother you with, you obtain that the number of available singles is precisely n times the average time of availability of the single. Okay? So this is the average number of available singles. Okay, and this is a very nice result, and as I said, mathematically it is an example of so-called ergodic result in which you essentially can move from average in time to average in space. It's Birkhoff type argument. Okay, so in this way, if you accept this fact, then we can return to this formula and replace the number of average number of available singles here by, well, this formula, which will create the average number of pairs per time to be, or contacts per time to be n times 1 minus yth squared. So here you can see that this is a difference with Holling. In Holling, it was a linear relation. Here you have an additional square here, because in some sense, to a certain extent, in epidemiology, prey and predator are drawn from the same population. So this is slightly different. Okay. Now, at a given time, if I take yth, this is the fraction of time any given individual is engaged in contact. Okay, because th is the average duration of a contact, and y is number of contacts per unit time. So it's number of contacts times average time. This is the total time an individual is engaged in a contact. And we use the same argument as before to claim that this is the average number of singles forming pairs, so average number of individuals forming pairs. Because again, if you are engaged in contact, it means that you are forming pair. You are engaged in this activity in average during this time, so using precisely the same argument, I can move from frequency in time to frequency in population. So the average number of singles forming pairs is precisely the total population times the fraction a given single is engaged in forming a pair. And of course, because I am looking at pairs, then I have to multiply everything by half. Okay, and then after algebra, I obtain for the number of pairs. So I have something like that. I replace now my conservation equation. Remember, physics rules. Conservation equation must be satisfied. Balance equation must be satisfied. So I obtain a quadratic equation for P, which I can solve. And after some algebra, I obtain that average number of pairs is given by this equation. It is not exactly the Holling equation. Holling equation would be if I had this removed. But qualitatively, this is the same formula. So essentially, the contact rate or the first term in the SIR model obtained using this argument is of this form. So this is the contact rate. You can actually, of course, simplify this n, but it is better to be written in this way, because here you can see that if n is very small, then this term, because of this one here, behaves like constant times n. So for small n, this function behaves as n. And if n goes to infinity, then, well, this term doesn't really interfere. So if n goes to infinity, then this fraction goes to 1. Okay, so then we obtain both types of forces of infection discussed earlier simply by looking at the endpoints of the spectrum described by this function describing general contact rate. Again, a model is like everything else. What you put in, you get out. So of course, this is under certain assumptions, like random mixing, which is not necessarily always true. It is also obtained on the basis of the fact that, you know, I'm either infecting somebody or looking for somebody to infect. And I can, for example, go and sleep. I can go, I mean, to engage in something leading to the Ricker equation. You know, it's a number of possibilities. Okay, so this is the second, in some sense, case study which I wanted to show you, is how to derive a Holding type contact rate in basic epidemiological model. And the last, I think I have still about 10 minutes, yes? So I will go through the last case. This is actually a model which, Alan Lloyd at the recent Pretoria meeting drew my attention to this actually. I had to do actually calculations myself, but I was not able to repeat his, to get his numerical values, but probably what I present to you is, well, at least I know how to justify this. And from his talk, I had only numerical values and some statements. So anyway, so the holy grail of epidemiology is R0, of course, as we know, we all know here. And this is essentially about mismatching models. So there's a very well documented example going, well, I think it was published in '78 in the Lancet, but later it was sort of like discussed by Mori. Even in the first edition of his mathematical biology book, he's discussing a number of basic texts on epidemiology. So it's a good example because, in some sense, it's a good example because it was very well documented because it was a flu in the dormitory, in some boarding school. So everything is perfectly well documented. The numbers are a little bit too small for our liking. It's 700 something individuals, so it's not really good for continuous modeling, but okay. So the epidemic lasted actually from 22nd of January to 4th of February, so short time. It seems that it was, again, clinical case of one infected boy moving into a host of susceptibles. Okay, so in this case, it is a very short period of time, so there is no point in putting demographics into this, because nobody died or nobody was born, especially in boys' dormitory. Nobody was born during this time. So we used, and following Mori, actually we use the standard SIR model and fitting data. These data are also taken from Mori. You obtain for SIR model beta equal to 2.2 more or less. Recovery time is very short actually, just 2 days. I cannot, but I don't dispute this, this is taken. And then this data give you the ratio, the basic reproductive number to be 3.8 more or less, 3.77. Okay? These actually are, this is also taken from Mori, I don't claim the authorship of this picture. So this is how the number of infectives was fitted. Well, everything is fine but the flu has sort of like so-called latent period. Okay, there is not, you are not immediately infective after infection. So in some sense, the whole model is wrong. How we incorporate delay or latent period? Well, there are very sophisticated ways of doing this, and I see that eventually Rashid Whiskey came to listen, and he's specialist in delay equations. So one of the ways to incorporate latent period is actually to consider a model with delay, with fixed or well, changing delay. But the brutal, trivial way is what already I think Abba and also Andrea showed. We simply introduce one more class, which is called exposed. So we consider, instead of SIR model, we consider the model with one more class in which you are infected but not infective. So essentially it is like an anteroom. You wait for some time. And well, there are proofs that if you do sufficiently many these classes and with different appropriately actually chosen sigmas, then such models will converge to models with normal delay, with real delay. But okay, so instead of, so let us go to our dormitory, and we consider a system of equations with the exposed class with latent period. And just the question, what has the latent period has on the progression of the disease? As in some sense the name suggests, it's latent. So it is actually delays the whole process. So in this picture, I think, no, it's actually taken from Lloyd's paper. This graph shows the progress of the disease in infectives for SIR model. Just a moment, okay, yeah?
0 is the time the single infected boy arrived.
Well, no, this is not dormitory. This is actually just a sort of like qualitative picture of the effect of.
They're trying to work out the phase difference. So the 0 is the start of the infection.
Yeah, this is.
When the initial infection arrives.
Yeah, at this moment, yeah. So I mean, but again, it is not. This picture is not related to the data in Morris' book. So this is the progress of infection without delay. This is the progress of infection with the latent class. So we see that it is a slower process. And because this will be important, and this is actually what Andrea said in his, I think, during the lab. What is important, what you can measure, is the initial spread of infection. So he calculated this, it was, I think, small r, and this actually, these two lines show the initial spread of infection, and essentially the infection spreads in a linear fashion. So this is for SIR model, and this is for the exposed class model, SEIR model. Now, so these two pictures are for the same coefficient, so for the same R0. Now, then we have actually to do reverse engineering here. Namely, if I have the data which are the same, and I want to fit two different models into this data, this will have a completely reverse effect. This will pump up all the coefficients through the ceiling. Because with the same coefficients, with exposed class, the disease progresses at a much slower rate. So if it progresses with the same rate as SIR model, then of course it must progress faster. So everything must be bigger. And this is actually true, and I will show you some numerical calculations in a moment. So this is actually how you fit SIR and SEIR model into the same data. Now we are back in the dormitory. Okay? And this is done just to sort of like preempt some assault. This is done in the following way, that we no, not we, they. They actually fit both models for the first half of the data, so up to 5, and then look at the forward sort of like prediction of this fitting. And you can see that actually both models give more or less the same type of description. SEIR is better at the end, SIR is slightly better in the second part. Okay? I was not able actually to repeat these calculations. This is actually taken from Lloyd's paper. But we can try to recalculate R0 for the same disease for SIR and for SEIR models by saying, okay, if these two models are the same, then the initial spread of the disease must be the same. So this small r, this linear part, must be the same. Yes, because the graphs here are the same. And r essentially is the slope of this curve here at the beginning. Yes, I will just calculate this r, sorry, it's here. Okay, so how we calculate r? This was already done in Andreas' lecture. So essentially what we are looking at, we look at the equation for infectives. Normally in the system of equations, here you have S. So this is a nonlinear part. But at the beginning, if you introduce only one infective, then for some time, practically you can put here the total population, or total population susceptibles, whatever you have here. If it was only one infective, then S0 was the same as N0. So in this way, at the beginning, the disease will spread according to the linear equation which is given here. And this gives you the formula for the initial rate of spread to be R0 minus 1 times mu. This is the formula which was given in the first lecture of Andrea, I think. You can do the same for SIR model. It's a little bit more complicated, but you can do this. In SERI model, we must actually look at these two equations. This equation is redundant. So we look at these two equations and we replace S here by N0 as before. Okay? And then we obtain that R is the dominant eigenvalue. For those who remember what is dominant eigenvalue, is the biggest actually solution of this quadratic equation. And you can factorize this. You can precisely calculate very nicely that R0 for SEIR model is given by this formula. So it is actually R0 SIR model times 1 plus sigma. So immediately you can see that if we try to fit the same model to a single disease, then of course R in both cases will be the same. Yes, because this is the same disease. This is observable. I calculate my R0, so I try to fit SIR model and for this R, and I will get something like that. Now I try to fit SEIR model to the same disease, and my R0, so the basic reproduction number for this new model, will be given by this formula. So it will be much higher. And actually the change is quite dramatic. Even if we add latency period of 1 day, then you jump from 377 to 8.3. So even, once again to emphasize, we have the same disease, we try to model this disease. We choose either SIR model or SEIR model. Observables are the same, but then any public health official would like to know what is R0. So now, a guy who is modeling this using SIR says, it's mild disease, 3.7. The guy using SEIR model says, no, hold on, it's 8. So the question is here, well, this is an example how sensitive are models on how strongly they depend on the practical choice of model for a given phenomenon. So it's quite important. I don't have any answer here. It's just sort of like a red light to switch on, to warn you to be very careful with choosing the right model to describe whatever you want to describe. And with this pessimistic point of view, I will finish. Thanks.
Questions? No questions.
No questions. Oh, good. Well, very first or very first for epidemiology?
The first equations that you wrote with two interacting species.
Ah, okay. This one? These two?
Yes.
Or these two?
No, no.
Okay.
Is there a real life example that follows those two equations?
Well, if for example, you are very close to the carrying capacity of one of the species, then, I mean, let us assume that in real life you would consider mass action. So you would consider P1 prime is equal plus some alpha 1 to P1, P2. If P1 is close to the carrying capacity, which is K2, sorry, P1, K1. So we are very close to carrying capacity, then nothing changes here, really. So it's one of the typical examples here. So it doesn't change. Of course, then you have to recalculate the coefficient. Yeah. And keep, of course, units correctly, yes. Because otherwise Henry will criticize.
No, but then you have to be symmetric. You should do the same in the second equation.
Well, yeah, no, in this case, yes. So, of course, this would describe the behavior in sort of like close to equilibrium.
Yeah, but then your 1 minus P1 already. Okay.
Well, this is very small then, because I mean the growth rate is very small, so it would be something like quasi-static assumption. No, I mean, I'm just giving an example. I'm not saying that directly from here you can. But in general, I mean, if you have any nonlinear interactions, if you are close to an equilibrium of one species or the other, then actually you can sometimes, well, this you can talk to Mylene because she knows what to do when you are close to, sort of like one equation is close to equilibrium. Then you make something which is in applied mathematics called quasi-steady or quasi-stationary assumption, and simply assume that one of the variables is constant, and then replace this variable in the first equation. Yes?
Yeah, so your example from epidemiology is very interesting to me. In ecology, often we have a variety of models, and then we fit them to data, and then we select which one is best based on the fit. But obviously, that could run into trouble. And so that makes me wonder what's missing. And is it something to do with when the first boy actually was exposed?
No, I think
that information were there, then
no, I think it is what is probably missing is lack of understanding of the underlying process, because it's not only. I mean, this is a simple example which I could calculate, but the first papers about similar stuff were written in, I think, 70s or 80s in some parasite. I can send you actually some papers on this, on some parasite behavior in organisms, and later they were picked up by Lloyd and by a few other people who did similar calculations. But so essentially, in my opinion, what is missing is lack of good understanding of the process.
But the thing is, often we use models to try to understand the process. And so we may not know, but we have data. So in a way, what you're saying is that this parameter associated with E is inestimable, in the sense that
there is
typical data set, you're unable to tell what the value is within.
I mean, there is unknown. this is an this is an unknown. We really don't know. We have to iterate this. So, I mean, things like that serve precisely to this point. Okay, somebody realizes that something is happening which shouldn't happen, and go back to drawing board and say, okay, what is missing in the model? Maybe something is missing in the model. So, as I said, I don't offer any answer here. I learned about this 2 months ago, and I think a week ago actually did calculations. So it's very fresh in my mind as well. So
I think there's a bigger theory of
yes.
estimability,
Yeah,
within
yeah.
which this lives.
Probably, well, I haven't seen. I mean, yeah, the stuff which is which I got from Alun is essentially just reporting things like that. There is no. They didn't try to find any theory. Because probably it would be something like, say, like meta theory, which would, you know, somehow a category theory in which you consider, I mean, you consider a class of models. Yes, it is beyond normal mathematics in some sense. This is my feeling. But as I say, it is very fresh in my mind. So I cannot really tell you anything more optimistic. Okay. All possible models, yeah.
All possible classes.
Yeah.
Maybe that's an issue.
It's okay. I think was Rashid first.
Could you please show that graph where you show I don't know, the number of infected cases, one with the exposed class and one without?
Okay.
The one that
Yeah. I know. And with initial rate of growth, yes. Yeah, this is SIR, this is SEIR. This is initial rate of grade for SIR, this is initial rate of growth for SEIR.
So just as a comment when you're closing up, when you say which value R you to believe, so at least when one is not sure which model to use and therefore which value R you to consider, this is one of the things that one must look at. The peak for the SI model is much higher.
Yeah, but these two pictures are simply taken. You take SEIR and SIR with the same parameters. So then you have something like that. The problem, for me, the problem is this picture, where you have essentially, you cannot say here that the peak in one is different than the other. Yeah. So this is reverse, as I say, reverse engineering. Which Abba, I think, was and then the new.
I was going to say maybe there's issues there may be issues with the data itself, because typically estimates for R naught seems to be too high from both models, like 3.77 and 5 point something. For influenza, we know the R naught value is probably between 1 and 2, even for pandemic.
So possibly that, yeah, because the R naught here is too high essentially, but yeah.
And maybe some of the boys were kicked in also. So
yeah, this is actually what Alun said. No, I mean, this was essentially what Alun said, that you know, the first boy was almost immediately put into the bed. So probably his infectiveness actually went down. So the rate of infection.
I would say the SEIR is more realistic.
Yeah, well, definitely from the modeling point of view, there is a latent period. So you cannot do SEIR. Sorry, SIR model. Sorry, I have been talking for too long actually. Okay, sorry. There are two questions. No, it was Cash was first, and so sorry too.
It'll be interesting to see from that perspective whether anything comes up. But yes, I had a question about the first term in these equations, the growth term, because you used your exponential and your logistic growth. But I've noticed some people using cubic terms.
In which
in ecology.
I mean, the very first part of the talk about ecology.
So in the first term in your equation, growth term.
Yes. Yeah. If you I mean, I said that it is the first set. If you want to build in Ali effect, yes, then you use cubic. You can use. I mean, there are others. There are also like Ricker or Pemberton-Holt type models. Also, you can fit there, but in some sense, if you open any textbook on differential equations which tries to do some ecology, some modeling, then usually you will see this set of equations. So they are the simplest in some sense, nonlinear. And that's
I think that the disparity in the two halves is significant in this case because the latent period is actually big compared to the time scale we are using. If, for example, if the latent period has been relatively small, for example, for HIV/AIDS, there's actually an incubation period, which is in days. And if you are now, if your model is in years, 3 days in 10 years will be.
this is completely different story here.
I'm just thinking.
Yeah, no. I mean, this is multiple scale problem, and ask Mylene about this. Here we are talking about essentially latent. I think the estimates are the latent period for flu is between 1 to 4, and the time of infection is, I think, 4 to 5 or something like that. Yeah. So I mean, here you have the same, and I deliberately have chosen the shortest latent period which is reported. So 1 day. If you take bigger latent period, then actually this will show, R0, I think, calculated one of the papers for this is something like 16. So it's even worse, for more or less the same period of recovery and latency. So yeah, but yeah, it's again, everything is model dependent here.
Yeah, it's model dependent. What I'm saying is that there are cases where we can actually overlook the exposed period because the time scale is relatively negligible in terms of what we consume. But for this case, the time scale is the latent period is quite significant because they are just days. This is 4 days, while the other is about maybe under weeks. So it is quite significant for the region. So in this case, it will make significant impact in the basic product.
You can see that if the latent period is going to 0 here, then everything collapses to the same R0. So yeah.
Yeah, but that may be a problem there also because sometimes even when you're within the latent period, you can still transmit it.
Yeah.
Even for flu, actually, toward the end of the latent period, you're actually transmissible.
I am a mathematician.
Yeah.